Hello everyone. Today I'll present our work, NS-Diff, Physics-Guided Video Generation via Reinforcement Learning, accepted at CVPR 2026. The core idea is simple. We teach a video diffusion model to respect physics. Today's video generators look stunning visually, but they struggle with physical realism, especially when simulating rigid bodies and fluids. Look at this clip from Sora. The prompt is, archaeologists discover an ordinary plastic chair in the desert and dust it off. In the Sora result, the chair, which is a rigid body, behaves like sand. It dissolves and crumbles. Our NS-Diff result, on the right, keeps the chair rigid throughout. This is exactly the kind of rigid, fluid confusion we set out to fix. Our solution rests on two simple physical principles. 1. For fluids, we apply a simplified Navier Stokes constraint to eliminate velocity field divergence, so fluid motion stays continuous and incompressible. 2. For rigid bodies, we apply a minimum jerk principle, which suppresses high-order motion jitter and improves temporal coherence. The challenge is how to inject these constraints into a generative model, and we do it through reinforcement learning. A policy network is rewarded when its denoising trajectory satisfies these physical constraints. Concretely, NS-Diff is composed of three modules. First, a noise-robust physics dynamics detector that analyzes motion directly inside noisy latent frames and separates rigid from fluid regions. Second, a physics-conditioned latent injection module that encodes the detected physics, velocity, deformation, material embeddings, and injects it into the DIT denoiser through cross-attention. Third, a reinforcement learning optimization module that imposes the simplified Navier-Stokes equation on fluids and the minimum jerk constraint on rigid bodies, using PPO with an adaptive gating scheduler that decides when to apply physics guidance. Let's zoom in on the detector. For rigid bodies, the key observation is that the relative spatial relationships among internal pixels stay constant. They follow an affine transformation. So we decode a low-resolution proxy with the VAE decoder, run AR flow to estimate optical flow, compensate global motion, and apply temporal smoothing. We then fit an affine model to every local patch P. If the residual is below a small threshold, the patch is labeled as a rigid region. The same pipeline is reused for fluids, but with a different criterion. Mathematically, fluid motion is characterized by high divergence or curl. We therefore compute the sum of squared divergence and curl over the flow field. If it exceeds a threshold, the patch is labeled as a fluid region. This unified detector works directly on noisy latents, that is the noise-robust part. Once we know which patch is rigid or fluid, we extract three pieces of information per patch: velocity field, deformation gradient, and a learnable material embedding. They are projected by an MLP encoder into physics tokens, which are fed into every DIT block via cross-attention. This way, the denoiser is conditioned on physics in addition to the usual text prompt. Finally, we treat the denoiser as a Gaussian policy network. Each denoising step samples an action from its noise prediction. Two physics losses act as the reward: a divergence loss enforcing the Navier-Stokes constraint on fluids, and a jerk loss enforcing minimum jerk on rigid trajectories. We optimize with PPO policy gradient updates, modulated by the adaptive scheduler so that physics is only enforced once denoising is reliable enough. Now the results. Compared with WAN 2.1, our method is clearly more physically realistic. Look at the close-up of the mango falling on desert sand. WAN 2.1 makes the sand cloud look static. Ours generates a believable splash. The same is true for the diver entering the pool and the red paint splashing onto a white wall. Compared with OpenSora 2, the gap is even larger on collision-rich scenes. The wine glass shattering, the footballer on a rain-soaked pitch, and the car driving through thick mud all look more physically plausible with NS-Diff. Quantitatively, we evaluate on three text-to-video benchmarks: PhysVideoBench, UCF 101, and WebVid. NS-Diff, red bars, achieves the lowest jerk error and the lowest fluid divergence, are two physical realism metrics, and at the same time the highest visual quality in terms of appearance quality, motion quality, and frame consistency. So NS-Diff improves physical realism without sacrificing, in fact, while improving visual quality. That's NS-Diff in a nutshell: a lightweight, physics-aware reinforcement learning layer on top of any latent video diffusion model. Thank you, happy to take any questions.